There is a beam of light leaving the sun right now, and by every measurement your instruments can make, that beam will take 8 minutes and 20 seconds to reach the Earth. Your clock will confirm it, my clock will confirm it, every clock in this solar system, ticking away in patient agreement, will confirm it. But there is one thing in this entire universe that will disagree, and it is the light itself. Because if you could somehow ride inside that beam, if you could shrink yourself down and sit on a single photon as it left the surface of the sun, no time would pass for you at all. Not 8 minutes, not 8 seconds, not a single tick of any clock anywhere. You would leave the sun and arrive at the Earth in the same immeasurable instant, because for light, departure and arrival are not two separate events. They are the same event, stitched together into a single frozen frame. This is not poetry. This is not a metaphor dressed up to sound profound. This is a literal, mathematically verified consequence of the equations that describe how our universe operates. And it leads to a conclusion so strange that most people never sit with it long enough to feel its full weight. If you were made of light, 13.8 billion years would not have passed since the birth of the universe. 0 seconds would have passed. The cosmic microwave background radiation, the oldest light we can detect, the fossil afterglow of the Big Bang itself, has been traveling for nearly the entire age of the universe by our clocks. And yet, from the photon's own point of view, if a photon can be said to have a point of view at all, it left the moment of creation and arrived at your telescope in the same breath. No aging, no waiting, no journey in the sense we understand journeys. The Big Bang, for light, happened milliseconds ago. Or more precisely, it happened an instant ago, because for light there is no elapsed time to measure at all. Before we go further, it's worth being honest about why this claim sounds like the kind of thing you'd find printed on a poster next to a picture of a nebula, sandwiched between quotes that were never actually said by the people they're attributed to. Physics has a bad habit of being hijacked by mysticism. People hear light doesn't experience time, and they leap straight to conclusions about consciousness, about the universe being a single eternal now, about ancient wisdom traditions somehow anticipating quantum mechanics thousands of years before Einstein was born. None of that is where we're going. What we're doing here is something closer to detective work. We are going to take a claim that sounds like folklore, place it under the same scrutiny you'd apply to a suspect in an interrogation room, and follow the evidence wherever it actually leads, using nothing but the physics that has already been tested, confirmed and reconfirmed by real experiments conducted by real scientists whose names and data you can look up yourself. The case begins in 1905, in a patent office in Bern, Switzerland, where a 26-year-old clerk named Albert Einstein was doing something patent examiners were absolutely not supposed to be doing with their time: rewriting the foundations of physical reality. Einstein wasn't working in some prestigious laboratory with an army of assistants. He was evaluating patent applications by day, and in the evenings wrestling with a question that had apparently bothered him since he was a teenager. One he later admitted had haunted him since he was 16 years old, roughly a decade before he'd actually resolve it. What would you see if you could run alongside a beam of light at the same speed it was traveling? Classical physics, the physics of Newton, gave an answer, but the answer was troubling. If you could match light speed, the light should appear frozen beside you, an electromagnetic wave stuck in place, oscillating nowhere. But Einstein knew from the work of James Clerk Maxwell decades earlier that light is not allowed to sit still. Maxwell's equations, which describe how electric and magnetic fields propagate through space, only make sense if light moves at one specific speed relative to everything, always, without exception. A stationary beam of light isn't just strange, it's mathematically forbidden. Something in the picture had to give. What gave, in Einstein's 1905 paper on the electrodynamics of moving bodies, was our assumption that time ticks at the same rate for everyone, everywhere, regardless of how fast they're moving. Einstein proposed two postulates. First, the laws of physics look the same for every observer moving at a constant velocity, no exceptions. Second, and this is the one that breaks everyone's intuition on first contact, the speed of light in a vacuum is the same for every observer, no matter how fast that observer is moving, and no matter how fast the source of the light is moving. It doesn't matter if you're standing still, driving a car, or sitting inside a spacecraft screaming through space at 99% the speed of light. If you measure the speed of a passing beam of light, you get the same number every single time. Roughly 299,792 kilometers per second. This single postulate, when you follow its logic all the way through, forces something has to bend to keep the math consistent. And what bends is time itself, along with space. This is the part of the theory known as time dilation, and it is not speculative. It has been measured directly, repeatedly, using atomic clocks flown on airplanes, using GPS satellites that require constant relativistic correction to stay accurate, using particles created in laboratory accelerators that survive far longer than their resting lifetimes would predict, simply because they are moving close to the speed of light. One of the earliest and cleanest confirmations came in 1971, when physicists Joseph Haefel and Richard Keating flew cesium atomic clocks aboard commercial airliners, circling the globe both eastward and westward, and then compared those clocks against a reference clock that stayed on the ground at the United States Naval Observatory. The airborne clocks came back reading a different elapsed time than the stationary one, and the size of that difference matched, to a striking degree of accuracy, the exact number predicted by relativity. This wasn't a thought experiment confined to chalkboards. It was cesium atoms on real airplanes disagreeing with each other about how much time had passed, exactly as the equation said they would. The equation that governs this effect is elegant and brutal in its implications. As an object's velocity approaches the speed of light, time for that object, as measured by an outside observer, slows down. Not metaphorically, literally. A clock moving at 90% of light speed ticks slower than a stationary clock, and the closer that velocity creeps toward the speed of light itself, the more dramatic the slowing becomes, until, at the speed of light exactly, the equation predicts that time dilation becomes infinite. Time, for something moving at light speed, does not merely slow down, it stops entirely. This is where most explanations of relativity quietly change the subject, because the equation technically breaks down at that exact point, and physicists are careful, appropriately careful, about drawing conclusions from an equation at the exact value where it produces a division by zero. But the case doesn't end there, because there is a more precise tool for asking this question, one that physicists actually use, called proper time. Proper time is the time experienced by an object along its own path through what's called space-time, the four-dimensional fabric that combines the three dimensions of space with the one dimension of time into a single unified structure. For any object moving slower than light, you can calculate a non-zero proper time between two events, the amount of time that object itself would experience. For light, when you carry out this calculation using what's called the space-time interval, the answer comes out to exactly zero. Not approximately zero, not a very small number that rounds to zero. Exactly, precisely, mathematically zero. Every single time, for every photon, everywhere in the universe, without exception. What this means, translated out of the mathematics, is that from the reference frame of a photon, if such a reference frame could meaningfully exist, the moment of emission and the moment of absorption are the same point in spacetime. There is no distance between them and no duration between them. A photon that left a star 10 billion light-years away and just now struck a detector on a telescope in Chile did not, from its own perspective, travel for 10 billion years. It did not travel at all. Departure and arrival collapse into a single event. This is what physicists mean when they say light does not experience time. It isn't that light experiences time very slowly, it's that the entire concept of experience and duration fails to apply to light in any way that resembles how we apply it to everything else in the universe. Now here is where the case gets genuinely interesting, because this isn't an abstract curiosity confined to chalkboards. It has a direct, staggering implication for how we understand the Big Bang itself, and for how we understand the light we can see with our own instruments right now, tonight, pointed at the sky. The universe, as best we can measure it, is approximately 13.8 billion years old. This number isn't a guess pulled from thin air. It comes from multiple independent lines of evidence that all converge on the same figure, which is exactly the kind of convergence that gives scientists confidence in a result. The rate of cosmic expansion, measured through what's called the Hubble constant, gives one estimate. The oldest stars we can find in globular clusters give another, consistent estimate. And the most precise measurement of all comes from something called the cosmic microwave background, a faint bath of microwave radiation that fills every corner of the observable universe, discovered by accident in 1965 by two radio astronomers, Arno Penzias and Robert Wilson, who initially thought the strange background noise in their antenna was caused by pigeon droppings before realizing they had stumbled onto the afterglow of creation itself. The cosmic microwave background is, in essence, the oldest light in the universe. It was released approximately 380,000 years after the Big Bang, at a moment cosmologists call recombination, when the universe had finally cooled enough for electrons to bind with protons and form neutral hydrogen atoms, allowing light to travel freely through space for the first time instead of being constantly scattered by a dense fog of charged particles. Before that moment, the universe was opaque, an impenetrable plasma soup. After that moment, light could finally stretch out and travel in straight lines, and some of that very first light, released nearly 14 billion years ago, is still arriving at our detectors today, stretched by the expansion of space into faint microwave wavelengths, mapped in extraordinary detail by satellites including the Wilkinson Microwave Anisotropy Probe, launched in 2001, and the Planck satellite, launched by the European Space Agency in 2009, both of which produced all sky maps of this radiation with precision fine enough to reveal tiny temperature fluctuations, differences of only millionths of a degree, that correspond to the seeds of every galaxy, every star, and every planet that would eventually form. By our clocks, sitting here on Earth, that cosmic microwave background light has been traveling for roughly 13.8 billion years. That is an unfathomable stretch of time by any human measure, longer than the existence of our solar system by a factor of 3. Longer than multicellular life has existed on Earth by a factor of more than 20. And yet, if you apply the same physics we just walked through, the same zero proper time that applies to every single photon without exception, that ancient light has, from its own frame of reference, experienced none of that. 0 seconds. The photons striking your satellite's detector tonight left the early universe and arrived at that detector in the same instant, by their own internal measure. Which is not really a measure at all, because there was no interval to measure. The Big Bang and this very moment, for that photon, are not separated by 13.8 billion years. They are the same event. This is the resolution to the paradox posed at the start of our investigation, and it's worth being precise about what it does and does not mean, because sloppy thinking here is exactly what turns real physics into pseudoscience. It does not mean that time doesn't exist. Time demonstrably exists, and it passes for you, for me, for every clock, star, and galaxy that isn't moving at the speed of light. It does not mean the universe is somehow all happening at once from some grand cosmic viewpoint, because there is no single universal reference frame from which to make that claim, and relativity actually forbids the existence of one. What it means is something more precise, and honestly, more interesting. The concept of elapsed time is meaningless for anything traveling at exactly the speed of light, because the mathematics that defines elapsed time, the proper time interval calculated across spacetime, evaluates to 0 for a light-like path every single time, without exception, for every photon that has ever existed or ever will. It's worth pausing here to address the skeptics in the room, because a good investigation always stress tests its own conclusions. Can we actually trust the postulate that light speed is constant for every observer? This isn't just Einstein's assumption taken on faith. It was tested directly, years before Einstein published his theory, by an experiment conducted in 1887 by Albert Michelson and Edward Morley, who built an extraordinarily sensitive interferometer designed to detect tiny differences in the speed of light depending on the direction it traveled relative to the Earth's motion through what physicists at the time believed was a stationary medium called the luminiferous ether. If the ether existed, light should have moved slightly faster or slower, depending on whether it was traveling with or against the Earth's motion through it, the same way sound travels faster with a tailwind than against a headwind. Michelson and Morley found nothing. No difference, no matter which direction they pointed their instrument, no matter what time of day or season they measured. The experiment became, somewhat famously, one of the most important null results in the history of science. A result that told scientists something was fundamentally wrong with their assumptions, years before anyone had the right framework to explain why. Einstein's postulate that light speed is constant regardless of the observer's motion explained the null result perfectly, without requiring an ether at all. And the predictions built on top of that postulate have kept being tested, kept being confirmed, for over a century since. In 2017, the case received one of its most dramatic pieces of corroborating evidence when two neutron stars, roughly 130 million light-years away, spiraled into each other and collided in a catastrophic event that produced both gravitational waves, ripples in space-time itself, and a simultaneous burst of light across the electromagnetic spectrum. Detectors on Earth, including the LIGO and Virgo gravitational wave observatories, along with dozens of telescopes around the world, captured both signals arriving within about a second and a half of each other, after traveling for 130 million years across the cosmos. That kind of agreement over that kind of distance placed extraordinarily tight constraints on the idea that gravity and light might travel at even slightly different speeds, ruling out entire categories of alternative theories in a single stroke. The framework built on Einstein's postulates, the same framework that tells us light experiences zero proper time, keeps surviving every test we throw at it. So where does that leave the investigation? We began with a title that sounds almost too strange to be real. The Big Bang happened milliseconds ago, if you're light. And the honest, evidence-based answer is that this framing actually understates the strangeness of the truth. It isn't milliseconds, it's zero. No time at all has passed, from the perspective of light itself, since the birth of the universe. That conclusion isn't a poetic flourish or a philosophical stretch. It falls directly out of special relativity, a theory whose predictions have been tested through atomic clocks on airplanes, particle lifetimes in accelerators, GPS satellite corrections used by billions of phones every day, and the arrival times of light and gravitational waves from a neutron star collision, more than 100 million light years away. Every one of those tests points in the same direction, and every one of them supports the conclusion that a photon does not experience the journey it appears to us to be taking. There is something worth sitting with in this idea, not as mysticism, but as a genuine recalibration of what we mean by the words old and ancient when we talk about starlight. When you look up at the night sky and someone tells you that you're looking at light that left its star thousands or millions of years ago, that statement is true. And it is also, from the light's own vantage point, meaningless. The photon didn't wait around for thousands of years to reach your eye. It didn't experience a journey at all. In some sense, every point of light in the night sky is not an ancient artifact slowly crossing the void toward you. It is an instantaneous connection between 2 points in space-time that happen, from our slower, mass-bound, thoroughly ordinary perspective, to be separated by an immense distance and an immense duration. We are the ones experiencing the delay. Light is not. There's a companion thought experiment that physicists have used for over a century to make this idea concrete, and it's worth walking through it here because it puts flesh on the bones of an otherwise abstract equation. Imagine a pair of twins. One stays home on Earth, the other boards a spacecraft capable of reaching a significant fraction of the speed of light, travels to a distant star, turns around, and comes back. When the traveling twin returns, they are measurably younger than the twin who stayed behind. Not symbolically younger, actually younger, in the sense that fewer seconds have ticked on their personal, biological and mechanical clocks. This isn't a paradox in the sense of being a contradiction, despite the name it's been given. It's called the twin paradox because it seems to violate common sense, not because it violates the mathematics. And the asymmetry is fully explained by the fact that the traveling twin undergoes acceleration, turning around partway through the trip, while the twin who stayed home does not. The effect has been confirmed in miniature using unstable subatomic particles called muons, created when cosmic rays strike the upper atmosphere. Muons decay so quickly in their own resting frame that by the standard non-relativistic calculation, almost none of them should survive the trip down to the surface of the Earth before falling apart. And yet, detectors on the ground register muons arriving in far greater numbers than that naive calculation predicts, because the muons are moving fast enough that time dilation stretches out their effective lifetime as measured from our stationary vantage point on the ground, letting far more of them complete the journey before they decay. Push that same twin paradox logic to its absolute limit, all the way to the speed of light itself, and the traveling twin wouldn't come back younger by a few seconds or a few years. They would come back having aged not at all, because at the speed of light, the very quantity used to measure aging, the proper time interval, collapses to zero. Light is the twin who never leaves the moment of departure, because for light, departure and every subsequent moment along its path are one and the same instant. This connects to a deeper idea in physics called the block universe, a way of picturing space-time not as a stage where events unfold moment by moment, but as a single, already complete four-dimensional structure in which past, present and future all exist as fixed coordinates, the way every point on a map exists simultaneously, even though you can only stand at one location on that map at any given time. This isn't universally agreed upon among philosophers of physics, and there remain genuine, unresolved debates about what the block universe picture implies about free will or the nature of now. We flag that debate honestly here, rather than pretending it's settled, because an evidence-based investigation doesn't paper over open questions just because they're inconvenient. But what is settled, what has been tested and retested without failure, is the underlying mathematics of space-time intervals that makes the block universe picture coherent in the first place. And that same mathematics is exactly what produces a proper time of zero along any path traveled at the speed of light. Light isn't moving through the block universe the way you or I move through a room. It is, in a sense physicists take seriously, tracing out a path along which no time separates its start and its end at all. This is also a good moment for what we call, on this channel, the reality check. The point where we separate the evidence-based conclusion from the versions of this idea that tend to spiral into nonsense online. You may have seen claims that this proves the universe is a simulation, or that consciousness and light are somehow linked at a fundamental level, or that ancient philosophical traditions predicted relativity through meditation alone. None of that follows from anything we've covered here. What follows is narrower and in some ways more remarkable precisely because it's testable. The mathematics of space-time intervals produces a proper time of zero for anything traveling at exactly the speed of light, a result confirmed indirectly through decades of experimental agreement with special relativity's other predictions. And this result means our intuitive language about light traveling and aging and taking time to arrive describes our experience of that light, not the light's own non-existent experience of the journey. Evidence-based reframing, not sensational mysticism. The gap between the strange headline and the actual physics closes completely once you follow the math instead of the mythology. There's one more piece of evidence worth entering into the record before we close the file, because it addresses an objection a careful skeptic would raise immediately. If light takes no time to travel by its own measure, why do astronomers constantly talk about looking back in time, measuring distances in light years, and mapping a cosmic horizon beyond which we cannot see at all? The answer is that every one of those concepts belongs entirely to our reference frame, the frame of observers embedded in a universe that has been expanding for nearly 14 billion years, and none of it contradicts what's true in light's own frame. When light leaves a distant galaxy, the space between that galaxy and us continues to stretch during the light's transit, a phenomenon called cosmological redshift, which lengthens the light's wavelength and lowers its energy the longer it travels through our expanding universe. This is precisely why the most ancient light we detect, the cosmic microwave background, arrives not as visible light, but as microwaves. It started out as much hotter, more energetic radiation, and has been stretched by a factor of roughly 1100 over the course of its journey through expanding space. That stretching is real, it's measured with exquisite precision, and it's a feature of the space the light traveled through, not a feature of any elapsed time the light itself experienced along the way. The observable universe has an edge, roughly 46 billion light-years away in every direction as measured today, not because light has been slowly crawling toward us for that long in some experienced sense, but because that is the current distance, accounting for cosmic expansion, to the farthest points from which light has had enough time, in our frame, to reach us since the universe became transparent. Every part of that description depends entirely on our clocks, our rulers, and our vantage point inside a specific reference frame. None of it requires light itself to be doing any waiting, and the zero proper time result we've been building toward this entire investigation holds exactly as firmly at the edge of the observable universe as it does for the sunlight warming your face. It's worth asking, as any good investigation should, what this means for how we understand the universe's earliest moments going forward. Right now, astronomers are pushing to see further and further back, using instruments like the James Webb Space Telescope to capture light from galaxies that formed within a few 100 million years of the Big Bang. Light that has been redshifted, stretched into infrared wavelengths, by the expansion of space itself over billions of years of travel. Every one of those ancient photons obeys the exact same rule we've walked through here. Every one of them arrives at Webb's mirrors having experienced, from its own frame, no elapsed time whatsoever. We are, in the most literal sense the mathematics allows, looking directly at the early universe. Not a faded memory of it, but a direct, unmediated, zero-delay connection to a moment in cosmic history, filtered only through the distance and the expansion that separates then from now in our own frame of reference, the only frame in which then and now mean anything at all. In 2022 and the years following, Webb identified candidate galaxies whose light appears to have been emitted only a few 100 million years after the Big Bang, pushing the record for the most distant confirmed galaxy further back than any instrument had managed before. And each new record announced in the coming years will be measuring the exact same thing. Not how long the light waited to reach us, but how far back along the same zero-duration path that light's journey actually traces. Every headline about a new, most distant galaxy ever observed is really a headline about our own position in spacetime relative to that emission event, dressed in language borrowed from a human experience of waiting that light itself never has and never will undergo. The case closes, as these cases always should, not with mystery restored, but with mystery resolved into something you can verify yourself. The equations of special relativity are public. The data from Michelson-Morley, from WMAP, from Planck, from the 2017 Neutron star merger. All of it is published, peer-reviewed and available for anyone willing to check the sources, rather than take the claim on faith. Light has existed 0 seconds since the Big Bang, not because the universe is mystical, but because the universe is precisely, rigorously, beautifully mathematical. And the mathematics simply does not permit time to pass for anything moving at the one speed the entire structure of space-time is built around. The Big Bang for light isn't ancient history, it's right now. It has always been right now, and it always will be.